So first topic, so I'm particularly interested in water. Being in Utah, obviously we should all be interested in water. So I want to think a little bit about, typo, sorry, I got to fix that. Solar water pasteurization, okay? Why is this important? It's a huge problem. Something like 20% of the world's population don't have access to clean drinking water. Even in the US, as I mentioned, in fact, I was in a reservation about a few weeks ago, and it is exactly like that. There's no access to clean water. Roughly half of the diseases are caused by this, especially in children. So this is a huge, huge challenge, especially deaths of children. So I think the motivation is very clear, but I don't want you to think about this more just as a humanitarian motivation, but think about this as if you can provide a solution to 20% of the world's population, there is clearly a business there. So this is not a nonprofit. When you think about innovation, it really needs to be sustainable, right? And that is the challenge. And to me, this is not a business challenge. It is really a technical challenge. And that's why you as engineers need to think about it that way. And I'll try to reiterate this point. It's quite important, in my opinion. We need more of this thinking. So what is the solution? We know pasteurization. What is pasteurization? Is simply, so you can pasteurize milk. I'm talking about water. So you can take water, heat it to about 149 degrees Fahrenheit, 65 degrees Celsius. It'll pasteurize the water. It'll kill the disease-causing microbes. It can make it drinkable, right? That's the whole point. The most important observation here is that you do not need to boil it. Boiling water is extremely expensive energy-wise, right? You have to take it from liquid to vapor phase. That is a huge, this phase transition is an incredibly expensive thing to do. You want to avoid it if you can. Anyway, so pasteurization, of course, is used in all kinds of industries. Yeah, milk is pasteurized at 71. And it's fairly short, right? You only need to do it for a few seconds, 15 seconds. And for water, it's, you just need to do 65 degrees Celsius for 60 seconds. So far, so good. Fairly simple. Okay. Now, I'm going to ask you this. I want you to spend 60 seconds, again, talk with your neighbors. Tell me, what is the problem you see with this? So you need to be able to identify problems, and then you can identify the solution. So that's the exercise here. And do the same on Zoom as well, but don't shut out the answers yet. I mean, there are no answers. I would just want you to identify. So please, I'm going to ask you guys. So. Sorry, I'm going to put you on the spot. What's your name? Yeah, okay. So you signed up for the in-person class?
No, I'm actually signed up for the online.
It's fine, yeah. You can still show up, but feel free to discuss. You turn around, talk to them if you want. Are you planning to attend the in-person?
On Wednesdays.
Yeah. Okay. So, yeah. So you can be included, yeah. I'm going to ask you. Anything you see?
Temperature and duration, right?
Yes, exactly,
So,
yeah.
Like, is it the most efficient way to do it is 65 or 60 seconds? I'm kind of thinking, maybe is it more energy efficient to do it warmer in less time?
That's a great point. I haven't thought of this. Interesting. So that is an optimization question. You're right. Yes. I don't know the answer. Yeah. Okay. Okay. Great. I'm sure people have done research on this, but I don't know the answer to this. It's a really good observation. Yeah. Yeah, this is a thermodynamics problem, so you should be able to do this. Yeah. Anything interesting?
Well, the obvious one is the energy, right, that you're going to have.
Yeah.
That's a statistical average that it'll kill that much. So
yeah.
You have to sample to see, okay, did you in fact, and so what will your sample size or verification be to do so? And
yes, you hit on something which I'll come back to, but go ahead. Yeah.
The other thing, once you kill it, doesn't mean you remove it. So.
Well, that's a good point. I don't know if you have dead bacteria in your body. I think it's okay because the macrophages will take it out. Yeah, that's my guess. Yeah, that's an interesting point. Yeah, right.
Purified in terms of particulate matter.
Yes. Yeah. Yeah. Probably this. That's a good point. Anyone else? No. Anyone wants? Fairly small. Don't be shy. I'm gonna ask you.
We commented on like the boundary, so like you have to heat it.
Yeah.
But also not vaporize the water before you heat it. So,
Oh, so you'd lose it, you mean?
yeah.
Yeah, okay. That's a good point. I didn't think of that either. But if you're, yes, that also hits the answer I was looking for. Although there's no right answer, but it's a good point, yeah.
Storing it, I mean, pasteurize it once, 20 days.
What happens, yeah. That's also a really important point, yeah.
Are you going to guarantee that it's safe in a plastic jug that you pour it into after you pasteurize it?
Yeah.
There's a lot of.
Yeah. That's a really great observation. Yeah, I mean, I think that's what they do with the milk, right? They have to package it carefully, yeah. Yes, exactly. So this has to be at the point of use, is my guess. Yeah. What's your name?
Aiden.
Aiden had a great observation. Do you want to say quickly?
Sure. So they have to be at 65 degrees Celsius for 60 seconds. Is that the most efficient way to do it? Is it more energy efficient to do it at a higher temperature but for a shorter duration of time?
Yeah, so the question there is there an optimization we can do in terms of the amount of energy that can be input into it, which I hadn't thought of. So all three observations, I hadn't thought of it, so that's great. But there is a glaringly obvious thing here. Yeah? Exactly. It's exactly the point, yes. Exactly, yeah. And both of you kind of alluded to this, but you hit the nail on the head. How do you know when you've reached 65 degrees? Interesting problem, right? If you want to do it, there is a technical problem. Hopefully, there's a technical solution. So this is what I want you to. I want you to think this way. Okay, it'll take some time, and you have to see a lot of examples. I don't do it myself, so I hope you will do this better than me. And there is a solution, so that's why I'm showing this as an example. So, oops. So they essentially created a temperature indicator. It's a wax that melts at 65 degrees Celsius. Very cheap, simple solution. Okay, they call it the water pasteurization indicator, and it simply melts. So essentially, all they do. So how do I send this?
The WAPI, or Water Pasteurization Indicator, is a simple device that indicates when water has been fully pasteurized. A plastic vial with the wax on the top and the washer on the bottom is placed in the middle of the pan. When water is heated to the pasteurization point, the wax melts and drains to the bottom of the vial. When cooled, the wax hardens again, and the WAPI can be turned over and reused again and again.
There you go. So that's a fairly simple technical solution to a simple but very obvious important problem, right? So these kinds of solutions are what I think, and it's very widely used, right? These are the sorts of solutions which I believe would be very cool if your team can come up with. Simple, doesn't need to be complicated. Okay, let's move on. So that's WAPI. Of course, there are other solutions, even simpler things, as we should know about this. Of course, we can use a solar cooker, heat things up. That's straightforward. If you will need a WAPI to know if you reach the temperature. And then, they basically, I'm not going to play this video in the interest of time, but basically they created something similar to a greenhouse where you essentially create a container which allows the sunlight to come in, but it has a black back surface that essentially heats up and the water heats up. And there are things you can do to improve it. In fact, there were some teams that worked on these kinds of ideas we can talk about later. And you leave it out in the sun. Of course, the simplest possible thing is just to take a bottle of PET, fill it with water, leave it out in the sun for a few hours. And the UV rays, because PET transmits UV, will kill most of the bacteria as well. So you have a two-pronged approach in this right? So there are lots of solutions. There's really simple solutions. You should always, this is why the literature review is important. So when you start thinking about these problems, you want to kind of see what people have done, what kind of roadblocks have they met, and really try to understand why is it not being used? Like why, if you go hiking out in Zion or whatever, but if you're backcountry or whatever, if you don't have water, and what do? I mean, you have tablets or things like that. Are there things, some sort of problems that you are familiar with, right? That you can try to solve. So it could also be from your own experience as well. And it's always better that way. I want to show one more example, and this is a bit more technological. They essentially create a light-driven hydrogel. So it's a hydrogel that is a material, so it's a material science innovation. It's a hydrogel that essentially reacts to sunlight, and it allows the water to essentially filter through it. So you can actually remove a lot of the pathogens. And they have actually, at least back in the day, I don't know if they still have it, they had a company called AquaPow. So I'm gonna quickly play that video. It's from some research at Princeton, but they make it large. I wanna speed up some.
Lack of access to clean water is a challenge that millions of people face every day. We have developed a new approach to water filtration that could bring clean water to millions of households around the world, especially those that lack access to infrastructure. I'm Rod Priestley, Professor of Chemical and Biological Engineering and Dean of the Graduate School. Our technology is designed to produce clean water using freely available solar energy. The device works like a sponge, soaking up only clean water and leaving behind the contaminants. What makes this approach accessible to millions of people around the world, however, is that the process is driven by the heat of the sun. Most solar-powered water filtration devices use sunlight to evaporate water, which is very time-consuming. Other methods require electricity or another source of power to pump water through a membrane.
At the heart of our device is a gel material that can change its structure as a result of change in temperature. At room temperature, the gel can act as a sponge, soaking up water. When the sun hits the gel to 33 degrees, it does the opposite and pushes the water out of its pores. When you leave the gel in the sun to heat up, it pushes the clean filtered water back out into a container.
To me, the most exciting thing about this work is that it can operate completely off-grid, both at large scales and small scales. This means that the technology can be assessed globally, including locations where low-cost, non-powered water purification is needed.
Okay, so let me go back to this. So that's a good example of a material science innovation. Of course, the key is that you have to make it really cheap and really accessible, but still have to make money, right? You need to have a revenue source to support it. But the idea is simple. It doesn't require anything other than the gel itself, right? So it's a good example. And I'm sure we don't have time, but you can imagine ways to improve it. You know, for instance, it could be part of your project.